today's Power Chat, we're going to talk a little bit about effective grounding. Effective grounding is used to prevent voltage rise on unfaulted phases during single line ground fault. IEEE 1547 has a requirement that we cannot allow the voltage rise to exceed any more than 138%. Effective grounding is very important in a three-phase system. During a single line to ground fault in an ideal effectively grounded system, the faulted phase does not move the neutral point of the system. When effective grounding is not achieved, the neutral of the system is moved, which means that the phase voltages can see an increase of up to 173%. So in a three-phase system, we use a number of different ratios to achieve effective grounding. This is the traditional ratio of using system impedances of zero and positive sequence networks. Another method is using the coefficient of grounding, where you're actually using the phase and line ground voltages. So whenever we have a new system and we're integrating DER into our system, the best step is to draw a simplified diagram, noting the sources, the grounding configurations and transformer configurations of those sources, such as the distribution system shown here, the PCC of the project with a single line to ground fault shown at the PCC, and then also the project. Now with the project, we're going to show just the simplified pieces of equipment that we're concerned about: transformers, transformer configurations, the generator. In this case, we're going to simplify it, showing a synchronous generator and the generator grounding configuration. Our next step is to draw the positive sequence network. Here we take our same transmission source going into the transformer of the substation, just one lump sum of the line impedance. Keep in note the same single line to ground fault at the PCC, and still showing our impedances of the lines. So here we have the impedance of the ground bank, impedance of the transformer, the impedance of the generator, and the second generator as well. Note that we have, in the positive sequence, the grounding bank is dead-ended. And we're also showing that, in this case, the breaker to the system is open, islanding the portion. Our next step is to note the zero sequence network. Here in our zero sequence network, we're also showing the respective impedances shown in the zero sequence, but this time we have to pay attention to our configurations. Our source is grounded, which means it has a connection to the ground plane. Our grounding bank is grounded. It also has a connection to the ground plane. Our transformers, however, were grounded Y, but delta on this, they're Y on the secondary. Our generators aren't grounded either. So you can see that the generator and the GSUs of the system do not have a ground source. The only thing that has a ground source in the project side is the ground bank. So it's very important that this impedance right here is noted in the calculations, and the positive sequence of the system is noted in the calculations. Note that this impedance can be no more than 3 times the equivalent of the positive sequence impedance. When these items are maintained in these ratios, no neutral shift occurs in the system, and thus no unacceptable voltage rise occurs in your system. And that is effective grounding. Next week, join us for mitigating voltage rise impacts from DER.